Professor Jung completed a doctorate in atmospheric physics at the University of Kiel in 2000. From 2001 to 2010, he was a scientist at the European Center for Medium-Range Weather Forecasts in Reading. After leaving this role, Professor Jung took up the post of Professor of Climate Sciences at the University of Bremen and Alfred-Wegener-Institute for Polar and Marine Research. His fields of research are climate dynamics with focus on polar regions, climate modeling, weather and climate prediction. His lecture topic today is uncertainty in regional climate change predictions. So in a way, all the questions you've had from the first half prior to lunch, he is the one who is going to answer all those questions. So please, a big welcome for Professor Dr. Thomas Jung.
Okay, thank you very much. Thank you very much to ICD for giving me the opportunity here to present a topic which is very close to my heart. And I have to start, and I don't usually like to do that, with an apology, because I mean a meeting like this really lives from the fact that people stick around and be able to talk and discuss. But I have been, and I'm still recovering from a rather sort of unpleasant flu, and that's why I sort of had to come in today and have to leave rather early. So I apologize for that. So the title of my presentation is Uncertainty of Regional Climate Change Projection. And I would give you sort of a little bit of a flavor of what climate scientists think we know about what's going on, especially on the regional scale. Just to give you an overview, I would like to give you a short motivation. Then we will be focusing on regional uncertainty. I mean, look at how large the estimates we sort of climate scientists are producing, how large they are. What are the different sources of uncertainty? I mean, if you want to improve estimates, or if you ideally reduce uncertainty, you need to understand what the origin, what the sources are. And I would like to discuss this a little bit as well. Discuss about some shortcomings, then summarize and discuss with you. Yeah, this is a plot, and I've heard here on my way to the lecture hall that the climate sensitivity has been discussed quite extensively this morning. And as you all know, climate sensitivity is sort of defined as the temperature change of global mean temperature when you double CO2. And what you see here is a so-called probability density function as a function of climate sensitivity here, from 0 degree change all the way to 10 degrees change. And here the probability. The larger the values, the more probable the occurrence of this value is. And what you see is here there are different estimates. They differ slightly, but the general message is very similar. You have a range of values. So obviously there is uncertainty when it comes to a parameter like global climate sensitivity. And what you see is that the uncertainty sort of, I mean, there is sort of an enhanced probability for occurrence of temperature increase of something like 2 to 5 degrees under double CO2. But there's also a chance, although the probability is low, that we have something which is called dangerous climate change. And the probability, as you see, is certainly not 0. So the big question is, where does this uncertainty come from? And the answer for these plots is very straightforward. There are feedbacks in the climate system which do lead to this uncertainty. What I've shown here is the change in temperature we would expect if the only thing which was happen would be a doubling of CO2, and then the atmosphere with its radiative transfer would respond to that. So we would be very certain that the change would be 1.2 degrees centigrade in global mean temperature. But the fact then that once temperature are sort of warming, that cloud cover is changing, for instance, and that the the cryosphere is changing as well, and this is all uncertain, that leads to the uncertainty. And it's nothing, you know, I think scientists, climate scientists, are as clever or as silly sometimes as scientists from other fields as well. It's just sort of inherent to the climate system that it's very sensitive to so small perturbation of certain parameters. What is also interesting to see is that the feedbacks in general, the existence of feedbacks sort of moves climate sensitivity towards higher levels, so increasing the climate change expected due to purely radiative effects. That brings me now to the next slide, where you can from which you can infer the three sources of uncertainty. But I need to explain a little bit. What we see here is the projected change in global mean temperature, here from minus 0.5 all the way to 4 degrees. And here you see time going from the 1950s all the way to the end of the 21st century. And then you see here in solid black, you see what the observations told us, and then what climate models tell us. And then you see here different curves. You see a set of curves which are red here. And this sort of the solid curve is the average of all these small curves here. And this is the outcome from a scenario called A2. So if it really should be getting, if emissions should increase considerably compared to today, then that is sort of the outcome we would expect. The green curve is business as usual. So if we wouldn't change a lot in our attitudes, and if we would be cutting down on emissions, that is here the scenario B1, then you see this family of curves. And then you see individual thin lines, and these are the responses. That's what the climate models, 15 different climate models tell us what would happen if emission would follow a certain scenario, like B1, A1B, or A2. So, and you see that for a certain, the blue curves here, for instance, the difference between the outcome of the projected climate change between different models is rather large. By the end of the 21st century, we're talking about a range of 1.5 centigrade or so. And then finally, you see all these wiggles here. It's natural variability, basically, decadal variability. And you can see that there are periods where the temperature is very high, but it can be just by chance due to the fact that we are in one of these high lumps here of natural variability. So basically, a short summary, there are three sources of uncertainty. One is internal variability. These are the wiggles here, if you like, the weather of climate, the ups and downs. Then there's uncertainty due to the fact, the scenario uncertainty, due to the fact that we don't know how humans are reacting or will be reacting in the future. And there is uncertainty because the response to what is being put in the air, into the system, the climate system, that it depends on the climate model we are using. So that brings me to my first short summary. There are three sources of uncertainty: internal variability, model uncertainty, and scenario uncertainty. The scenario uncertainty is outside sort of what a climate scientist can do. I'm quite optimistic that we will be able to reduce model uncertainties in the years to come, and to some degree we will be, I guess, able to reduce the uncertainty associated with internal variability. So how large are these uncertainties, and can they be reduced? I mentioned this a little bit already a second ago. So what is the relative importance of these three sources of uncertainty? Here on the y-axis you see the uncertainty measured in terms of a variance, total variance, and here you see the lead time in years. That is basically spanning here the 21st century. And what you see are three different colors. There's orange here, it's very small. That is the contribution of uncertainty due to internal variability. These are the ups and downs in the climate system. And then we have the blue curves, the blue part here, which is due to the fact that our models are not perfect. And then here we have the scenario uncertainty, given the fact that we do not know what's going to happen in the future. And you see here that the uncertainty, the total uncertainty, the sum of these contributions grows exponentially, basically. And that especially at the end of the 21st century, the fact what humans will be doing to the climate system will be the key factor in determining what's going to happen. And in a way you could argue that is good news. If we do have such a big influence potentially on what's going to happen at the end of the 21st century, then it tells you that there is potential of doing something. But I think there's a problem seen in this curve as well, and that is if we start to cut emissions, the impact of the reduction of this green part here will only be seen in a few decades from now. And I think every government which is going to put hard measures there to curb emissions, will see the benefit only something of 20 or 30 years later at the earliest. And of course, that's something which is rather challenging, when it comes to implementing these things. And what you also see is here a zoom in the first 20 years. These are global values here. And here you see the uncertainty for annual mean temperature and here for decadal mean temperature. So if you make a prediction of the global mean temperature for 1 decade ahead, it shows you basically that the uncertainty is much larger than you want to predict the climate for a certain year. It's just because when you want to predict the climate for a certain year that the internal variability here, as shown in orange, is much higher. And then there's another fact usually that when you go from global scales, so when you go beyond the question what's happening to global mean temperature, when you go to regional scales, say what's going to happen to temperatures over North America, that uncertainty rises as well. And in fact, I think we are mostly interested, most of us, what is happening in a certain region. Sort of global mean temperature is sort of something very abstract for many and a little direct social relevance. But what we are interested is in how temperature changes in a certain place, how sea level changes in a certain place, and how, say, precipitation changes in a certain place. Right. Then, sort of, again, just looking sort of how the uncertainty here changes as a function of time here, the total uncertainty, sort of the larger the value, the larger the uncertainty of the global mean decadal mean temperature changes. And what you see is that sort of for the first 40 years or so, we have a decline in uncertainty. And that's just because the internal variability doesn't play a role anymore. And then sort of we have a maximum of certainty or minimum of uncertainty sometime around 2040, and then our uncertainty is going to rise again. And that's simply because we don't know how humans are going to react to the threat of global change. Now that brings me to regional differences. They're sort of the main theme of my presentation. And what is shown here is now not uncertainty, but it is certainty. Here it's the left panel here. And here you see the y-axis. Here's the so-called signal-to-noise ratio. A signal-to-noise ratio sounds very, very sort of complicated, but a signal-to-noise ratio of 1, say, tells you that the signal you are interested in, climate change, is as large as the noise. So the ratio basically is 1. If your signal is larger than sort of the background variability, which is not due to sort of humans, then you will be having a number higher than 1, and below 1 is usually rather low when it comes to confidence we are having. So what you see is, again, the fact that sort of the biggest signal occurs for global mean temperature around 2040. And again, here it is highlighted that when you look, for instance, for temperature change over Europe, the British Isles, or even Greenland, that our certainty or sort of the uncertainty decreases, or our certainty decreases. And here's the map of our certainty. I mean, here the larger, the redder the values, the more certain we are that humans are going to increase temperatures. And what you see is that most of sort of the confident areas lie in the tropics and in the subtropics. There we are most confident that humans will increase temperatures. The uncertainty increases if we go towards the mid-latitudes here in the polar regions. And this is largely due to the fact that we don't fully understand the working of the feedbacks in these regions up there. And the fact that the uncertainty is so large over here, these polar regions, where lots of the ice shelves lie, which when they melt would have a sort of a huge, potentially a huge impact on sea level, is certainly something which is a little bit disturbing. And here just briefly the regional differences, how the different sources of uncertainty, how they change here internal variability, model uncertainty, and scenario uncertainty for different time horizons. That is for the next decade, that is for 2040 to 2050, if you like, and that's the last decade of the 21st century. And where you see blue, basically, the uncertainty is very low, and when you have red values, the uncertainty is very high. So when it comes to the next decade, as I mentioned, whether we are going to cut emissions or not will hardly have an impact, not during the next 10 years. But it will certainly have an impact, something like at the end of the 21st century, and especially somewhere, when it comes to confidence in the tropics and the subtropics. And what we see is here that especially here the model uncertainty is dominating in the middle of the fourth decade here, and also at the end of the 21st century. So that tells us basically that when we improve our climate models, we could potentially reduce uncertainty of climate change projection of temperature locally quite substantially. I've spoken about temperature change. I mean, in principle, all the statements I've just made depend on the parameter and region you are going to consider. And I mean, generally what we find for precipitation is that the uncertainty is much higher. And this is due to the fact, as indicated by the increase in this orange area, that the ups and downs of the climate systems, the natural ones, are going up. They are much more dramatic and important for precipitation than they are for temperatures. Saying that the climate system is perfectly capable of producing long-lasting droughts and wet periods just due to internal processes of the climate system. Then I would like to come a little bit towards structural uncertainty. I mean, I've given you estimates here, how the uncertainty is. And the big question is, how good are these estimates? And I mean, these estimates were based on climate models, you know, and people, you know, it's debatable how good the models are in representing all the various aspects of things. And so I think what could be said is, if the climate models would be capable of sort of predicting what happened in terms of climate change during the last 30 or 40 years, then we would certainly be confident. It wouldn't be proof, but we would be confident that what the models are capable of doing is correct. And I think in many aspects, models are able to do that, but there are certain aspects where they aren't. And I would like to give you one very prominent example, and that is the decline of Arctic sea ice. I think, as most of you might have heard, is that we had very extreme reduction of sea ice extent in the Arctic here during the last 30 years. So what you see here is the Arctic, the extent in million square kilometers here as a function of time. And in black here you see the observations. And you see a dramatic recline in the area, sort of a retreat of the ice edge, if you like, during summer here in the observations. And then here you have the last summer here with the year 2012. And then you see the outcome here from blue, and with this shading, it sort of gives you the range of outcomes from different models. These are the old models, if you like, the ones which contribute to the assessment report, which has been published a few years ago. And these are the brand new ones, which will be feeding into the next assessment report. And what you can see from this here is that even, I mean, there seemed to be sort of an improvement, but clearly the observed decline, none of the models is able to represent. And in fact here, the observations lie clearly outside the range of what the models projected for the last 40 or 50 years. And that's certainly something which is worrying and which the climate research community needs to address to increase the confidence in our models and our predictive capabilities. That brings me to another aspect. Perhaps one of the most important parameters people are interested in is sea level change. And what you see here is a time series of global mean sea level. And it is so important because it affects such a high number of people on this planet. And what you see is here global mean sea level here in meters as a function of time. Again here black solid is the observational record with the observed 20 centimeter increase in sea level during something like the last 120, 30 years or so. And then you see here again projections, and again you see this uncertainty, which is rather large, ranging from sort of values of staying close to 20 centimeter increase all the way to 1 meter or more. And then you see this red arrow here, and basically the red arrow is sort of a little bit like a question mark, you know. I mean, people realized when they put this graph in there that in these estimates they didn't account for possible meltdown of the ice sheets over Greenland and Antarctica, because they believe it might be important, but they didn't account in the models for this process. Sort of they put this arrow up. So what about those ice shelves? There has been a study recently by a colleague of mine here in Nature where they looked at the ice shelves in the Weddell Sea. So for those of you who are not so familiar with the geography of Antarctica, we have here a map. This is Antarctica. Here you see the southern tip of South America. And then here the West Antarctic Peninsula. And this is Weddell Sea here. And here you have sort of a zoom in of Weddell Sea. Blue indicates the depth of the ocean. The bluer, the deeper the ocean. And what you see is here basically that there is a shelf of relatively sort of low ocean depth of 500 to 1 kilometer or so. And what is very particular, sort of special about this location is that we have two ice shelves here. So basically the ice masses of Antarctica are flowing downhill basically, and then they go onto the water, and then they are called, then up there on land they are called ice sheets, and then once they are drifting on the ocean they are called ice shelves. And you see here, that is the edge of the Ronne ice shelf, and that is here the edge of the Filchner ice shelf. And what you see is that a lot of these, I mean, these ice shelves are huge. So a really large area of ocean is lying underneath those. And at the moment we are quite fortunate that the currents are going sort of here along the rim, you know, and they are not entering here underneath the ice shelves. But what Helmer and others found was that this is probably going to change in the future. So they carried out model experiments, and then they found that basically in the end of the 21st century, here you see now temperatures. Here you see the warm temperatures of the open ocean, of the Southern Ocean, and here the cold temperature on these shelves, which are in contact with the ice shelf. That these cold waters are replaced increasingly by these warm waters from the open ocean. And then so they're flooding underneath the ice shelves into the cavities. So what is the impact of this? Does that matter? A 2-degree change in the temperature of the ocean? Just to give you an idea, the projected increase in the melting of these ice shelves in Weddell Sea is to go from 83 gigatons per year to something like 16,000 gigatons. So it's an increase of a factor of 20. So I guess most of you, not a lot of you, are sort of a minority might be familiar with gigatons. I also have to sort of convince myself always what that means. So let's put this into perspective. The current total loss of Greenland ice sheets amounts to 240 gigatons per year. So this increase here is a massive increase over what we are currently observing over Greenland. This increase would would lead to an additional sea level rise of 4.4 millimeter per year. So more than 4 centimeter per decade, which is quite substantial, especially if you compare this with the fact that currently the observed total sea level rise amounts to 3.2 millimeter per year. And that includes the effect, the dominant effect of thermal expansion. If you warm the open, the water is expanding and therefore sea level is rising. So the pure effect from this small region of the world ocean can lead to a larger increase than what we currently observe. And that is rather worrying and needs to be represented in those models when it comes to the future projections. And it is very worrying for people living on small islands, say in the tropics and in the subtropics. And they are sort of the most worried people, at least I know in my community. They are more worried than the Inuits to some degree when we are sort of, I mean, me as a polar researcher, when I go to conferences, because, you know, even an increase of something like 1 or 1.5 degree will mean a lot to these small island states. That brings me to the summary. I mean, one very important point to make is that uncertainty is inevitable. And that is nothing bad or something weak science or whatever. Uncertainty is there. We have to deal with that, and we have to learn to deal with that. And what is very important as well is that every forecast needs a statement of its accuracy, how uncertain we are. And a lot of thought needs to be put into this, because it's very important that the uncertainty you attach to your forecast is correct. It's very important to realize that the uncertainty depends on the parameter you are considering, whether it's temperature, precipitation, or sea level, and the region which is being considered. It is fair to say that for some aspects the uncertainty is quite large when it comes to sort of change in precipitation, sort of extreme precipitation events over Europe, or the hurricane frequency over the United States. But it's always important to keep in mind that even low probability predictions are useful to some. I mean, an example is if you were at an airport and somebody tells you that there's a 1% chance that the aircraft will be coming down on that fly, you would say the risk is too high. The probability is low, but the risk, losing your life attached to that, is very high. So this low probability will presumably for most of you be sufficient not to board. It always, you know, low probabilities might not be useful for some users, but they might be for others. And so a very important aspect is also that uncertainty doesn't necessarily mean that you don't need to do something about this. And then my personal view, progress in climate research. I mean, it's very important, and the community realizes that we do need to provide realistic estimates of the uncertainty. So that basically when you get a probability that you know that is pretty much the right one. Coming back to my example with the plane, you know, I mean, if someone tells you the probability that the plane is going down is 0.01%, then you better, you hope that this is the right estimate and that they are not completely wrong. You know, you have to work to make good and reliable and sort of meaningful decisions. You have to have the right probabilities. We do need to improve our models, and certainly we do need to provide decadal predictions to also sort of reduce the influence from natural variations. And that brings me to the end. Thank you.
Thank you, Professor Dr. Jung. I have a lot of questions because I'm very interested in this topic, so I will lead off, but please follow up with me. I have first a question regarding, do you have any map or data if I make the comment that let's assume it's 4 millimeters per decade?
Yeah.
What happens to my friend's country, Holland, Dubai, and Japan?
I mean, what you would like to have, I mean, what kind of map exactly, what the parameter? I mean, whether we have maps of local, regional sea level rise?
Yeah, if we assume that there's a 4 millimeter decadal rise, what happens, say, it will give us a better picture of what's happening around the world.
Yes.
If you told us what would happen to these three places.
Okay, I can tell you roughly what will be happening. 4.4 millimeter per year in almost every place. It's the same. It's a little bit like, you know, you are adding water, and if you add water in a certain region, you know, the water level, I mean, the signal propagates rather quickly across all the global ocean. And so basically it means first order that this projected sea level rise will be observed everywhere where you are. Of course, then there are sort of complications. Then there might be the land might rise or might go down. There might be local aspects to that. The ocean circulation might be changing in response to this sort of increase in fresh water, and that might lead to small alterations. But I think the 4 millimeter per year would be a pretty valid statement for almost every place on this Earth.
The other point I would make is that even a small error in judgment or prediction or probability would accumulate over time and could lead to very large changes.
Yes, that's absolutely right. I brought one figure which has been called, well, it's an uncertainty growth. I think it is even, in its original form, it is even called more dramatic uncertainty explosion. And what you see here, that I think sort of touches on what you were saying. I mean, when you look at the different forms of uncertainty, I mean, to start with, we don't know how much greenhouse gases they are going to emit. So we have an uncertainty here. Then we have, you know, because we don't fully understand the feedbacks, we don't know exactly sort of, I mean, how this translates into global temperature change. So we have an increase in uncertainty here as well. But then we are not very interested in global change. We are interested in what's happening at the local scale. And usually sort of the uncertainty becomes much larger on local and regional scales as well. So we have another increase over here. And that's not where the problem stops. You know, I mean, once I tell you with certainty that temperature or let's say precipitation will be increasing by 2 millimeters per year at a certain place, what does that mean to people? You know, then you have to make assumptions. What does happen, say, to the river levels? What does happen to flooding and so forth, you know? And then this is a range of possible impacts adds another level of uncertainty. With what you come up at the end is a rather large total uncertainty. That's right.
Thank you.
I think I can just do that. For the recording,
So my question is actually based off of this model here. Why is it that the global climate sensitivity has a smaller deviation than the regional scenarios on that level?
I mean, are we more certain about global aspects, about global climate change than about regional climate change? Is that your question?
Yeah, exactly.
I mean, the regional climate change is much more sort of superimposed, affected by natural variability. You know, you have sort of, in the North Atlantic, you have sort of the overturning circulation, you know, the meridional overturning circulation, which leads to sort of decadal scale changes. You have something similar in the Pacific, you have something in the Indian Ocean as well. If you look at these basins, the level of variability is quite large. If you average over the globe, you know, one of the phenomena might be going up, the other might be going down. Sort of you average over them and the uncertainty goes down. You know, it's like in statistics when you have sort of random variation. If you average about them, uncertainty goes down with the 1 over the square root of n. It's a little bit like that.
Okay, cool. Thank you very much. That makes sense.
More questions or comments? Thank you then. Thank you, Professor Jung.